We'll continue today in section 3.3 on logarithmic functions, and if there's time, we'll start section 3.4 on properties of logarithms. At about 11:35, we'll start the Zoom meeting. So join the Zoom meeting and make sure that your camera is on, and then I'll send you the quiz through email. We'll read over what we already read last time on logarithmic functions. So let b be a constant real number such that b is greater than 0 and b is not equal to 1. And recall that y equals b to the x is the base b exponential function of x. The domain of y equals b to the x is all real numbers from negative infinity to positive infinity, and its range is from 0 to infinity, excluding 0. And we observed that the exponential function that has the form y equals b to the x is a one-to-one function. That means its inverse is also a one-to-one function. And the inverse function of y equals b to the x is the base b logarithmic function y equals log base b of x. So that means that the domain of y equals log base b of x is the set of all positive real numbers from 0 to infinity, and its range is the set of all real numbers. And then the definition of log base b of x. Log base b of x is the exponent that b is raised to in order to produce x. So if we mimic the definition, then we can say b raised to the exponent log base b of x produces x. Okay, it's to understand logarithms, it's helpful to know that a logarithm is equivalent. A logarithmic equation is equivalent to an exponential equation. So for this part, let's just let capital B be greater than 0, such that capital B does not equal 1. Let capital A be greater than 0, and let capital P be any real number. Then these two equations are equivalent. This logarithmic equation, log base b of a equals p, is equivalent to the exponential equation b raised to the exponent p equals a. The two equations contain the same information, but one equation is logarithmic and the other equation is exponential. So we'll do a few exercises where we convert logarithmic equations into exponential equations. Log base 5 of 125 equals 3. Since 3 is equal to the base 5 logarithm of 125, then 3 is the exponent that 5 must be raised to in order to get 125. And you'll no doubt agree that 5 to the third equals 125 is true. The logarithmic equation that it came from is equally true. Log base 3 of 81 equals 4. Convert that to an exponential equation. The base number 3 raised to the exponent 4 equals 81. In the next example, log base 7 of 7 equals 1. Convert that to an exponential equation. The base number 7 raised to the exponent 1 equals 7. For this one, log base 2 of 1 is 0, equals 0. The exponential equation equivalent to that is the base number 2 raised to the exponent 0 equals 1. Okay, now we'll do it in the other direction. we'll convert exponential equations to logarithmic equations. 2 to the 6th equals 64. We know that's true. To convert it to a logarithmic equation, well, note the base of the exponential. The base is 2. So the base of the logarithm is also 2. The exponent is 6. So the logarithm has to be equal to the exponent. And then the argument of the logarithm is 64. One thing you can do a 3-point test to verify that your logarithm is correct. The base raised to the number on the right-hand side of the equation has to equal the argument. So 2 to the 6th equals 64. So we have just verified that we have the right logarithmic equation. Okay, 3 raised to the 5th power equals 243. The base is 3, so the logarithm has base 3. The argument is 243. The logarithm is equal to an exponent, and this particular exponent is 5. Okay, and the next one, 4 to the 2nd equals 16. Convert that to a logarithmic equation. The base 4 logarithm of 16 equals the exponent that 4 must be raised to in order to get 16. And then the next example, 6 to the 3rd equals 216. So the base 6 logarithm of the argument 216 equals 3. That's all there is to it. If you know how to go back and forth, then that will be useful, very helpful. Okay, we'll evaluate some logarithmic expressions in Objective 2. Okay, evaluate logarithmic expressions. We'll use this equivalence property if b, m, and n are real numbers, where b is greater than 0 and b is not equal to 1, then b to the m equals b to the n implies that m equals n. So this equivalence property has to do with exponential terms. So how are we going to use that when evaluating logarithms? Some of these, if you know much about logarithms, some of these you can tell what these simplify to or how to evaluate these right off the bat. But we'll go into a little more detail. So log base 3 of 27, well, it has to equal something. So I'll just say that it equals m. Whoops. I don't know if I want to use the same letter as I'm using up there. So how about log base 3 of 27 equals a. And then if we convert this logarithmic equation into an exponential equation, the base number 3 raised to the exponent a equals 27. And you'll recognize 27 as a perfect third power. 3 to the 3rd is 27. So I'll write this as 3 to the a equals 3 to the 3rd. And now we can use this equivalence property. So this is like b to the m equals b to the n implies m equals n. So 3 to the a equals 3 to the 3rd implies the exponent a equals 3. But this exponent a is equal to log base 3 of 27. So in other words, 3 is equal to log base 3 of 27. Okay, this is a little more writing than is absolutely necessary. So on this one, this time I'll use x. log base 5 of 625 equals x. Convert this to its exponential equation equivalent, 5 raised to the exponent x equals 625. But 625 is just 5 to the 4th. And so if 5 to the x equals 5 to the 4th, then the exponents are equal. X equals 4. And x is exactly the number that we were trying to find. So in other words, log base 5 of 625 equals 4. Okay, so no doubt you see what's going on, but we'll do these other ones just for practice. Log base 7 of 1, that's equal to something. I'll just say it's equal to w. Then convert this to an exponential equation. 7 raised to the w equals 1. But 1 is the same as 7 to the 0. And so if 7 to the w equals 7 to the 0, then w equals 0. So in other words, log base 7 of 1 equals 0. Okay, so as long as the base of the logarithm is what it's supposed to be a positive number that's not equal to 1, then anytime the argument of the logarithm is 1, then the value of that logarithm is 0. Okay, log base e of e, the base e logarithm is the natural logarithm, so it gets its own special notation. Okay, but you can say log base e of e or the natural log of e, it's equal to something. Let's say that it's equal to y. Then convert this to an exponential equation. The base number e raised to the exponent y equals e. But e is just e to the first, and so y equals 1. Okay, the next ones, we're going to be doing the same sort of thing, only that inside the arguments are fractions this time. So log base 5 of 1 over 25. So that's equal to something. Let's call it x. And then 5 to the x. 5 to the x equals 1 over 25. But 1 over 25 is 1 over 5 to the second. And 1 over 5 to the second is 5 to the negative 2. So 5 to the x equals 5 to the negative 2. That means x is equal to negative 2. Or in other words, log base 5 of 1 over 25 is equal to negative 2. Okay, log base 6 of 1 over 6. So let's say it's equal to y. Then convert the logarithmic equation to an exponential equation. 6, the base number 6 raised to the exponent y is equal to 1 over 6, which is 1 over 6 to the first, which is just 6 to the negative 1 power. So if 6 to the y equals 6 to the negative 1, then the exponents are equal according to the equivalence property. So that means log base 6 of 1/6 equals negative 1. Okay, I'm sure you got the hang of this by now, but let's do the remaining two. Log base 4 of 1 over 64. Let's say that it's equal to c. So convert this to an exponential equation. The base number 4 raised to the exponent c equals 1 over 64. In the denominator, 64 is 4 to the third. And so 1 over 4 to the third is 4 to the negative 3. And so if 4 to the c equals 4 to the negative 3, then c equals negative 3. So in other words, log base 4 of 1 over 64 equals negative 3. Okay, the next one, the natural log of 1 over e to the 5th. So I'll do this one a little differently. 1 over e to the 5th is e to the negative 5. And remember that the natural logarithm is the base e logarithm. So this natural log of e to the negative 5, this is equal to the exponent that e must be raised to in order to get e raised to the negative 5. So that means this has to be equal to negative 5. The base number e that isn't written with this notation, it's still there. The base is e. E to the negative 5 equals e to the negative 5. Okay, a couple of terms that you need to be aware of. The common logarithm is the base 10 logarithm. And you can write log base 10 of x, but whenever you see the log notation without the base, it's understood to be the base 10 logarithm. Your high-powered calculators have the base 10 logarithm key on those. And then we've already discussed the base e logarithm that's called the natural logarithm. The base e logarithm, the special notation is ln for the natural log. So this is always known to be a base e logarithm. And your calculator also has the natural log function. Okay, in objective 3 in section 3.3, apply basic properties of logarithms. We'll have more advanced properties of logarithms in section 3.4, but these are basic ones. So learn these first. Let b be greater than 0 such that b does not equal 1. And the following are the basic properties of logarithms. Log base b of 1 equals 0. We encountered this thing earlier, but you can verify it. B raised to the exponent 0 equals 1. We know that's true. Any non-zero number raised to the exponent 0 is 1. And we also saw this situation today already. Log base b of b equals 1. So this means the same thing as the base number b raised to the exponent 1 equals b. We also know that's true. The basic property number 3, we've also encountered this. Log base b of b to the x equals x, because the base number b raised to the exponent x equals the base b raised to the exponent x. And then basic property number 4, well, this is just the definition of the logarithm. Log base b of x is the exponent that b must be raised to in order to produce x. This has a condition, though, that the x value that is the argument of the logarithm must be positive. Okay, so we'll apply those basic properties in these 4 examples. Log base 9 of 9. Let's see, 9 raised to the first power equals 9, so 9 to the first equals 9. So that means log base 9 of 9 equals 1. 11 raised to the exponent log base 11 of 19. Okay, the base 11 logarithm of 19 is what 11 must be raised to in order to get 19. This is just an application of this 4th property that involves the definition. Log base 5 of 1. 5 raised to what exponent equals 1? So 5 to the 0 power equals 1. And log base 4 of 4 to the exponent, which is the square root of 37. So what must 4 be raised to in order to get 4 raised to the square root of 37? It has to be raised to the exponent square root of 37. Okay, the next objective in section 3.3 has to do with graphing logarithmic functions. So we'll look at some preliminary information first. So let b be a positive real number such that b does not equal 1, and let capital P be a real number. And consider the logarithmic equation p equals log base b of a. Okay, so the base of the logarithm is capital B. Capital A is referred to as the argument of the logarithm. It's whatever number or expression that you're computing the logarithm of. And P is equal to the base B logarithm of A, so that means P is the exponent. Okay, and we've seen this before. Since capital P equals log base B of A is equivalent to A equals B to the P, it follows that capital A is greater than 0. If the base number B is positive, then you can raise that number to any exponent from negative infinity to positive infinity, and it will still be positive. Okay, so the important thing to remember by this is that the argument of a logarithm is a positive real number. So for a logarithmic equation like this one up here, whatever number goes inside the argument, it has to be greater than 0. Okay, that will be a useful fact to remember. Okay, so the foregoing information will help us when graphing logarithmic functions. So for this one, I'll just let the base number b be greater than 1, and we'll sketch a graph of what y equals log base b of x looks like. And we'll give the domain and range, the intercepts, and the vertical asymptote. And then also find the inverse function. Okay, so first let's find the domain. The argument of the logarithm is x, and remember what we said about arguments of logarithms. Arguments have to be greater than 0. They have to be positive. So the interval notation for the domain then is parenthesis 0, infinity. The range turns out to be all real numbers. Okay, so I'll just do a rough sketch of the graph. If the base number b is greater than 1, well, when x is 1, we know log base b of 1 is 0, so the x-intercept is the ordered pair 1, 0. The domain is x greater than 0, so the vertical line x equals 0, which is just the y-axis, that's the vertical asymptote. And then the graph is going to look something like this. If you remember on a previous page, y equals log base b of x is the inverse function of y equals b to the x. And if b is greater than 1, y equals b to the x looks something like that. So this upper graph is y equals b to the x. And we also mentioned, this was also mentioned, that whenever you graph a function together with its inverse function, the two graphs are symmetric with respect to the line y equals x. So the graphs aren't perfect, but hopefully you'll get the idea. Okay, so how do you find the inverse of y equals log base b of x? So we'll do that now. Find the inverse of y equals log base b of x. Well, I already wrote down what the inverse is, but what's the step-by-step procedure? This step-by-step procedure is what you do for all one-to-one functions when you want to find its inverse. Step 1, so this will help you review for today's quiz. Step 1, write y equals log base b of x. Step 2, interchange x and y. That is, replace y with x and replace x with y. And then in this step 3, solve the equation in part 2 for y. So solve for y. So regardless of the one-to-one function that you're trying to find the inverse of, in step 3, after you've interchanged x and y, in step 3 you solve the equation above for y. Well, the only way that we know how to solve x equals log base b of y for y is to write down the exponential equation that is equivalent to this logarithmic equation. And we've practiced this a few times today. Okay, so the base is b, and b raised to the exponent x equals the argument y. So in other words, y equals b to the x. This is what I get when I solve this logarithmic equation for y. So this is the inverse. Okay, here's another reminder. I think I told you that I would remind you of this repeatedly. So log base b of a equals p, and b to the p equals a are equivalent under the right conditions. Capital B has to be positive and not equal to 1. Capital A has to be positive because arguments of logarithms are positive. And p could be any real number. Okay, so y equals log base b of x and b to the y equals x are equivalent. So that means if you convert this logarithmic equation into its exponential equation equivalent, you get this equation because b to the y equals x. Okay, the last thing we'll do today before the quiz is graph a logarithmic function. Okay, so log base 4 of x, the argument is just x, so the domain is x is greater than 0, so the domain is all positive real numbers. And so the vertical asymptote, I'll just write v dot a. The vertical asymptote is the y-axis, but the equation for the y-axis is x equals 0. Okay, and we can learn how to pick ordered pairs strategically. Since the base of the logarithm is 4, well, how about if I pick x to be powers of 4, like 4 to the first. So let's find what the y value is when x is 4. So log base 4 of 4 is 1. So when x is 4, the y-coordinate is 1. Well, the next x value that's of interest to us is when x is 1. And let's see, log base 4 of 1, 4 raised to what power equals 1? 0. And we can only pick positive numbers. Let's just pick one more power of 4. 1/4 is considered a power of 4 because it's just 4 to the negative 1. And when x is 4 to the negative 1, log base 4 of 4 to the negative 1 is negative 1. So this will get us started, I guess, on graphing logarithmic functions. We'll just plot those ordered pairs. So 1, 0 is a point. That's the x-intercept. 1/4, negative 1, and 4, 1. So I guess I should label these so that it's more clear. So the graph looks something like this. Okay, so the ordered pair 4, 1, 1, 0, and 1/4, negative 1. And why don't we find the inverse step by step? 1, write y equals log base 4 of x. Step 2, interchange x and y, so we get x equals log base 4 of y. In step 3, solve for y. Well, we can do this in one movement. 4 raised to the exponent x equals y. So y equals 4 to the x is the inverse. Okay, so why don't we stop there, and I'll go to my office and then I'll email quiz 9.